Hey everyone, today we're going to discuss how to classify acids and bases, different ways to classify them, and what makes acids fundamentally different than bases. In order to do this, we will have to take a small history detour. Before any formal definition for acids or bases had been created, and when scientists were only just beginning to study chemistry experimentally, they were able to recognize acids and bases. They noticed how they reacted differently and saw patterns. For example, scientists saw that acids have a tart or sour taste, while bases have a more bitter taste. Also, bases tend to feel more slippery. All the scientists of that time could recognize an acid or a base when they saw one, but none of them could describe an acid or a base in general. They didn't know what was actually different between the two, and so the race to find the answer was on. The first clue came when they realized that all acids contain hydrogen. This development turned out to be not as significant because although all acids have hydrogen, not all hydrogen-containing compounds are acids. But this idea of hydrogen ions did lead to the first formal definition of acids produced in the 1880s. A Swedish chemist by the name of Svante Arrhenius realized that when acidic solutions are added to water, they form hydrogen ions in the water. And when basic solutions are added to water, they form hydroxide ions. This makes sense when you look at the fact that the sour taste of acids comes from the hydrogen ions, and the bitter taste of bases comes from the hydroxide ions. This simple reaction shows the formation of hydrogen ions in solution after a solid acid has been added to the water. So scientists finally had their first definition of acids and bases, but it did have its limitations. The Arrhenius definitions of acids and bases only applies to aqueous solutions. In order to encompass all solutions and create a more accurate definition of acids and bases, a team had to be assembled. So, in 1923, Johannes Bronsted of Denmark and Thomas Lowry of England created the Bronsted-Lowry definitions of acids and bases. Instead of looking at the presence of hydrogen ions, Bronsted and Lowry chose to look at the transfer of hydrogen ions. Bronsted-Lowry definition of acids and bases states that acids are proton donors while bases are proton acceptors. If we look back at our example with the HCl and water, we see that the HCl donates a proton to the water, making HCl our acid. The water in this reaction has accepted the proton from the hydrochloric acid to form a hydronium ion. This makes water our base. Now that we have our two definitions for acids and bases, we have to compare them and see how they work with each other. Although the two definitions are similar and both involve hydrogen ions, they are different and lead to compounds being classified as both an acid or a base on different occasions. In order to see this, let's look at a reaction of ammonia and water. Our water donates a proton to the ammonia to form ammonium. This makes our water a Bronsted-Lowry acid because it donates a proton. This works out and makes sense because the ammonia has been added to water to produce more hydroxide ions in solution. Our ammonia is therefore the Arrhenius base, and knowing that an acid and base must always work together, we see that we have one acid and one base in this reaction. But when we go back to our reaction of hydrochloric acid and water, we see that water has gained a proton. By gaining a proton, water is a Bronsted-Lowry base, and the HCl, which donated that proton, is now our Bronsted-Lowry acid. When the two reactions are compared, we see that the water can act as either an acid or a base depending on what else is in the reaction. This quality makes water amphiprotic, or a substance that can act as